Okay, let me say, we will have a math club. This is like crazy weekend, right? There's homecoming and there's a science thing, but there's a math club too, Friday at 5. Keisha Cook, who some of you may know, who is a pretty new faculty member, she always gives really good talks. She's going to talk about making math posters from scratch. This might be useful for some of your graduate students. I know that a lot of you are getting to the place in your career where it's more talks than posters. However, you're also, many of you are probably going to be mentors someday, and so there'll be probably some good, there'll be some good points there. So I would highly recommend that. Okay, and I'll probably give you all an assignment or something. I'll probably be caught up by then. Next Wednesday, like a week from today, I'll be out of town, so there won't be a class. This is what we were working on last time, and we did half of this. When are we a Hilbert ring? Number one, every homomorphic image of R is a Hilbert ring. And number two, either R is zero dimensional or has infinitely negative quantities. By the way, I should point out that, of course, these two are not mutually exclusive. You can have zero-dimensional ring that has a whole ton of magpie ideals. Let me point out, zero-dimensional also means that every time ideal is in fact maximal, right? So that might explain why such a thing would tend to be a Hilbert ring. So last time we did one. So let's move on to two here. Let's suppose that the dimension of R is positive and R is G domain. If P is a non-maximal prime, then R mod P is a Hilbert ring. So take a non-maximal prime here. Then mod P is a Hilbert ring. With finitely many maximal ideals. But since R1, so I'm going to call it R mod P something. Since R1, which is what I'm using for R mod P, it's a Hilbert ring. And in fact, the domain, right, because P is a prime ideal, right? With only finitely many maximal ideals, say M1, M2, Mn. The only G ideals are these maximal ideals. But the radical of 0 is the intersection of all these maximal ideals. Since R1 is a domain, there must be a many of them. Right, the radical of 0 is the intersection of these maximal ideals, since they're the max. Since the radical of 0 is the intersection of the G ideals contained, and this is it. But this is impossible with only finitely many, because R is a domain, and for example, take x1 out of M1, x2 out of M2, and xn out of Mn. That product is actually in the intersection of these ideals. And can't be 0 if R is a domain. So there must be in many of them. So let me make one last proposition before we're actually going to get the Nullstellensatz. And this one's kind of important, as you will see. We're dealing with one with multiple variables. Proposition. R is a Hilbert ring. If and only R. That's cool, because what this means is Hilbert rings are actually preserved not only under homomorphic images, but under polynomial extensions. And in fact, the homomorphic images help us out here. This direction is not too bad. You know, Rx is Hilbert. Then, so is Rx modulo of the ideal generated by X, which is isomorphic to R. By this result here. Every homomorphic image, Hilbert ring is a Hilbert ring. So R Hilbert. That's not too surprising. Usually in such a theorem, I would expect polynomial to the coefficient ring will be the easy way. How about the other direction? For the other direction, suppose that R is a Hilbert ring. And Q is a net. In Rx. Now, we know that R is Hilbert, Q is some G ideal up here. Our burden is to show that Q is maximal. That's what it means to be a Hilbert ring, that all the ideals are maximal. So what we're going to do is contract Q down to R. So I'm going to do this trick that I've done before by passing through the quotient. So let P be the contraction of Q down to R. This is a prime ideal. And we're going to pass to the quotient. Pass to the quotient. And so we can assume that P is 0. Right, so take your G ideal and consider R mod P. Right now, Q is G ideal. Q mod PX is Q mod PX is now the G ideal, and R mod PX. So what we've done is we passed to the quotient and considered this easy case. Assume P is 0, and additionally, R is a domain. So we pass from considering R and Q and RX to considering R mod P and Q mod PX and R mod P of X. So now we've replaced R by R mod P. So now we've got the extra added bonus that we can assume that R is a domain. Now consider, so now we've sort of restarted the problem. And we have R as a domain, and R is a domain, and Q is a G ideal in RX that contracts to 0. So now Q intersect R is 0 ideal. Consider the sort of the canonical homomorphism from RX. The natural map. And remember, our goal is to show that Q is a maximal ideal given by so so really, this canonical map takes X to the coset X plus Q, right? X plus Q, and we're going to let the my notation is, instead of writing out the cumbersome cosets, I'm going to let U be the image of X under this homomorphism. RU is a G domain. RU is a G domain. As Q is H ideal. So from earlier result, R is a G domain, and U is algebraic over R. From an earlier result we did. Since R is a G domain and a Hilbert ring, The norm must be. So. So RU is isomorphic to RX mod Q. This is a field, this is a field, therefore. And this establishes it because we've shown we want that in RX, any G ideal is maximal. Okay. Any questions? So I've used the word Nullstellensatz a couple of times. Let's actually formally state this. I'm going to do this in two parts. Theory. Or sometimes it's called Nullstellensatz. If K is algebraic and closed, and we have n indeterminates, then indeterminates. Then any maximal ideal n is only this is a very strong theorem. So this tells you for a polynomial ring over a field in n variables, if the field is algebraic or closed, exactly what the maximal ideals look like. Right? This deteriorates rapidly as you remove assumptions. Even if you remove algebraically closed, it can be bad. So for example, right? Q, of course, is not algebraic closed. X minus 2 are maximal ideals, but so is and these are all maximal ideals, right? Notice QX is principal ideal domain, so I would expect all my ideals to be principal. But these are all examples of maximal ideals, and as you can see, sort of very few of them in a certain sense are actually linear polynomials, right? By the way, how did I know this one was irreducible? That's right, it's an isosceles polynomial. And of course, it's bad enough if you take algebraic closed off the table. If you take a field off the table, it gets much, much worse. Maximal ideals of Z-X are, maximal ideals of Z-X are all pre-generated, but they require constants. Let's do second part. Nullstellensatz, the sequel. Let K be algebraically closed. And let's see, F G1 GR big polynomials. And invariables with coefficients K. If F vanishes at all the common zeros of G1 and GR, if F vanishes at all common zeros of G1 GR. And let me just make clear. That is to say, if G A1, A2, AN equals 0, if GI for all I between 1 and R, then F of A1, A2, AR. So that's what I mean by advantages of common zero. If you can plug these in and it kills all the GIs and kills F as well, then F, a power of F lies in the ideal. So F is in the radical of the ideal power. Then F to the K is in G1, G2, GR for some numbers. That is to say, F is in radical G1, G2. So this is where our work will pay off a little bit. What we've been doing as far as getting this out. So let's go through the proof, both parts of the Nullstellensatz. Number one, note notice that this actually I only want to go to -1 because I'm going to use it. So x1, x2 up to xn -1 is a Hilbert ring, and so we now consider Rxn. This is by our previous result that bar is a Hilbert ring, so is polynomial extension. And of course, this is actually polynomial ring over K and n variables. This is a Hilbert ring. If we let M be a maximal ideal of Rxn, maybe I have to see if it's going. and N is contraction to R. That is to say, N is equal to M intersect R. Then N is a G ideal. And since R is a Hilbert ring, it's max. And so, what do we get from that? Well, by induction, by the way, base case is pretty easy, isn't it? Because the base case is just KX1, and since K is algebraically closed, all the maximal ideals have to be generated by linear polynomials. It's PID generated by a polynomial that has to be linear. So by induction, we have N is of that form, and R mod N is isomorphic to K, and so also algebraically closed. Which is algebraically closed. And so, since the quotient is algebraically closed, M remember this one, M is generated by N and one more element. And in fact, since it's algebraically closed, it will be of that form. And so this is X1 minus A1. Xn minus A1. So we're done with that. So there we use all the tools here. Now we're going to do this thing about the radicals. So for part 2, since F vanishes on all common zeros of G1, G2, GR, then F is in every prime ideal, or every nice one. Then F5 in all maximal ideal. That contains GR. So F is in the radical of D1, D2. And again, it's because it's a Hilbert ring, so the radical of that is basically just all the G ideals that contain this, which is all the maximal ideals that contain that. And that's all we need, really. Okay, any questions on it? Yes.
Which part do you like more? Let's leave right. Let's move on right answer.
Probably, for me, the second part's a little bit more obvious, so I like the first one a bit more. Yeah, sorry to disappoint. Okay. Any questions? Okay, so now we're going to talk about, this is actually one of my favorites. So I like this more than either. Okay, so the first thing I'm gonna do is, so the Nullstellensatz, we talked about maximal ideals. And in services, prime ideals and polynomial rings under. Right. And so the maximal ideals are nice, for algebraic fields. However, prime ideals, in general, polynomial rings can behave in a more mysterious way. And we're gonna, investigate this a little bit. The first thing I'm gonna do is introduce something called the dimension, or the Krull dimension of a ring. How many of you all have ever heard of the Krull dimension? Right, and you heard Alan Loper complain about it a little bit at the conference, right? And you know, there are many notions of dimension, right? So if you're a Carey student, you might have heard of projective dimension or something like this. And there's a dimension is usually when you attach it to something mathematically, it's usually measuring size. Vector space, sort of how big it is. And Krull dimension is one way to measure the size of a ring and sort of how big it is. So I'm going to start off with this. When we count a dimension, we always start at 0. We say the chain of prime ideals Pn. And I do want those containments. So there's two things to note about this chain of ideals. Number one, I want them all to be prime. And number two, I want these containments to be strict. We're going to call this half length. Yeah. So we start counting at 0. If P0 was just naked by itself, we'd say it has length 0. We define the Krull dimension to be the supremum over the length of such chains of primes and R. So, let me look at some examples here. If that's field, it's dimension of 0. Dimension of Z equal to one. Can you generalize this? Something more general than Z? Bigger class determination.
What's up?
Your class.
Yeah, I can.
There you go. There you go. How about that?
Cool.
Anybody want to guess this? I bet I can say how many is higher. Question is, how high can I say? This one's two. Because there's all kinds of stacks here. You can do that. Or you could actually climb that way. And there's other stuff. Oops. I guess my little pictures here make it absolutely clear that the dimension of ZX is at least two, right? But how do you know that you can't stack them higher? Well, for now, let's just say I said so, right? But you can't for this one. But actually, it's interesting because this shows that a UFD can have dimension higher than that. If you want to guess what happens here? Um, here are a couple interesting things. Here's an example. What's that? Any finite ring. That's dimension zero. Okay, that's 21. Yeah.
Well, I mean, obviously, if we have a domain, then we have a field, so we have dimension zero. And then,
Okay, right, and yeah, that's a good point. So you can already beat me on the psychology. Some finite rings are fields, dimensions are fields of zero, so if there is a universal answer, it has to be zero, but.
If you've got a prime ideal, then it has to be maximal, because if you mod out by it,
There you
you
go.
end up with a finite in an open.
R mod P is a domain, and it's also finite since R is finite, right? Therefore, R mod P is a field. And so, P is maximal. So any prime ideal is maximal, so all things are one to zero. Right? I think that's kind of pretty. Can anybody give me an example of an infinite ring of dimension zero that's not a field? Here's the easiest one. Uh, looks like a lot of dimension there, but it's not out by. So basically what this ring looks like is it's polynomials over F and then pulling many variables, but all the variables are square and nil code, right? So in this ring, so let me write this way. I'm using the notation that where x I squared equals 0. All I. Let me point out the ideal generated by x1, x2 bar. This ideal is actually prime, and it's actually maximum, because when you mod out by it, you get a field, right? Agree? So if you take F to join with those XI bars, you mod out by all the XI bars, you get a field. So that's maximal ideal, and it's the only prime ideal. Can you explain why? Now that thing has only one prime. That one. What can you say about every one of those XI bars? There's something very powerful and potent you can say about them.
Every maximal ideal because the mill radical is, they're all contained.
Every one of these is nilpotent, right? So every one of these has to be in every prime ideal, and this ideal is maximal, so that's it, baby, right? This is it. So there's only one prime ideal, it happens to be maximal, and it's 0 dimensional. Here's another one. I'm gonna throw this out just for fun, I'm gonna prove this. This is due to, I believe, Gilmer and Heinberg. Yeah. Or then the product you know what, yeah. So what happens when you take a direct product of a 0 dimensional ring? What do you get?
Focus something interesting other than 0.
That's right, it is interesting. It's either 0 or infinity.
Nice.
No middle ground at all. And actually, if that's a finite direct product, it'll always be 0. And sometimes a direct product can be 0, even if it's infinite, but it's bananas. Okay, so let me ask you another question, and too many mushrooms or something, I don't know, but I can't remember if I asked this before, but let me ask you this. Is it possible to have an Ethereum ring that's infinite dimension? I remember what the dimension is, it's a soup over like stacks of prime ideals, so to speak. So, and I seem to remember that Ethereum rings satisfy the ascending chain. Can one have a ring that is infinite dimensional still in Ethereum? Well, let me give you an example. Suppose I have this one. as written, this one is not finite dimensional. I'll give you an infinite stack of prime ideals, and there's infinite many of them. All those ideals are prime. Right, and it's infinite dimensional. And in fact, you have an infinite stack of prime ideals, right, for sure. And this ring is not Ethereum, because in fact, the maximum ideal generated by X1, X2, X3 forever and ever is in fact an ideal that's not finite generated. So here's one thing that's true. You have no hope of building an infinite dimensional Ethereum ring this way. Can't do it because you can't ever have an infinitely, I mean, that's an infinitely ascending chain of primes, right? Infinitely, you can't even have an infinitely ascending chain of ideals, right? Which is much easier. So what if you could do this? What if for every positive n, you found a stack that's n high? Of course, there's still no guarantee. But let me outline this really quick because this is one of the greatest things ever. It's essentially the same as this ring is in localization. Actually, I think it's better index scale, right? Notice that you have countably many variables just like you have here, but I'm just trying to index them cleverly. Let P in right, let P in equal the ideal generator of the C. So I let P11 generated by that. P22, P33, P10, let S be the union P I one infinity. Now, look at R localized this. Only primes provide live in the PIIs. Agree? And notice these are all finitely generated. There are some details to be shown, of course. For example, all the primes, this says all the prime ideals inside this are singly generated for the whole thing. Right? All primes in this are finitely generated all the way up. So when you localize, all the primes are finitely generated. So this localization gives you an Ethereum ring. And notice, this is length Z, this is one prime, then you can go X21 up to P22. You can go generated by this, these two, and these three, P3. And you can make an end stack generated by this, all the way up to the end pair. So now you can build these stacks arbitrarily high, although never infinite, and all the primes are finite to generate, so it's Ethereum, it's infinite dimensional. This example, I believe, is due to the guy, it's incredibly clever. And I did skip some details there, but that, I think it's kind of good for your culture to introduce you to that, some things are rather strange. We'll talk more about this next time. Any questions? Okay, well, we'll catch you all on the flip side then.
It's false and that stuff, I don't use.